Okay, so this design problem here, I'll let you read it. We're actually designing the exact same parameters for the filter that we did in a couple videos ago. So we're designing where I have omega C1 being 100 rads per second and omega C2 being 10 kilorads per second. So I'm doing the exact same thing, but now I'm doing an ROC bandpass filter. So remember, when we did the cascaded RC filters, we just used omega C1 and omega C2 to get the components directly. But remember, we have these ugly equations for omega C1 and omega C2. Trying to figure out what I'd have to pick two values for R and L and then find C or something, and those will look like a pain to try and solve. So what we're going to do is we're going to use the simpler equations, and again, at the end of the video, the simpler equations are these right here. These are the simpler equations to use for an ROC circuit, and even this one you can use too, but it's primarily going to be these two. Well, let's think about this for a second. We can compute the bandwidth, because that is just simply 10,000 minus 100, which is 9,900 rads per second. Okay, so this needs to be equal to R over L, because that, again, going back up here, that's the equation for the bandwidth. And then we can compute my center frequency, because this is the square root of omega C1, omega C2. So this would be the square root of 100 times 10 kilorad. Well, let's go ahead and do that here. So 100 times 10,000, and then we want to do a square root of that. And actually that turns out really nice. That's just 1,000. And so omega 0 has to be 1,000. And this is where sometimes with these designs of ROC circuits, it's hard to sometimes get 100% realistic values for the components here. But we'll see what we can do here. So I like doing the omega 0 first, honestly, because this is then equal to 1 over the square root of L times C. Okay, so let's go ahead, and I like to, as I said, for some reason I like to start with that one. 1 over the square root of L times C. This is supposed to be equal to 1,000. So L times C is equal to 1 over 1,000 squared. So squared 1 over, so 1, 2, 3, 4, 5. So this is 1 micro. 1 micro, 1 mu. And so my L times C needs to be that. And that's where, okay, yeah, we're going to get some unrealistic values for the capacitors and inductors in this case, because, if I were, for instance, if C was 1 microfarad, L would be 1 Henry, which is kind of unrealistic. So what we'll do here is we'll kind of split the difference here. And what I mean by split the difference is we'll say, okay, well, we'll let L be 1 millihenry, which is actually not unrealistic. Or actually, maybe let's do 10 millihenry, which isn't unrealistic. It's still a fairly large value for it. But then we say, okay, well, then I've got C times 10 millihenry is equal to 1 micro. So C is equal to, well, what I do there, clear this out, 1 exponent 6 negative divided by 10 milli, and that's 0.1 milli, so this would be 100 microfarads, or 0.1 millifarads, which isn't horribly unrealistic. So actually, we got something somewhat realistic. So we have L is equal to 10 millihenries, and C is equal to 100 microfarads. So we've got that done. And that was just from the, now we have the bandpass portion, because remember, my bandwidth is equal to R over L. So my bandwidth was 9,900, which is going to be equal to R over 10 millihenries. And this is where some of these designs become a little unrealistic because, well, let's look at what the size of the resistor we're going to get here is. Okay, so 9,900 times 10 milli would be 99 ohms. Which isn't horribly unrealistic, so actually this design isn't too bad. But we're done now. And so we have my design, drawing my circuit. V in plus minus V out. This would be a 99 ohm. This would be 100 microfarads. And this would be 10 millihenries. And so we're done. But notice how different this design was than the one where we cascaded. Because even though we are given the exact same parameters, we wanted to compute different things because using those, and I'm going to go back here, using these equations for omega C1 and omega C2 for an ROC circuit design would be a pain in the butt to do. So what we do is, even if we're given omega C1 and omega C2, since we can compute the remaining parameters, we can get simple things for beta and omega naught. And one final thing I want to point out to you here. I'm going to go back here. Look at this transfer function. So it turns out that the transfer function is equal to beta times S over S squared plus beta times S plus omega naught squared. And again, why is it important to recognize this? Any transfer function in this form is a bandpass filter. So if we came up with another circuit and it had the same transfer function like this, it's another bandpass filter. Alright, let's end here.